Remind you that we start from acids, so we start from H2SO4. It will split into 2H plus and 1SO4. Here the charge is plus 1, here the charge is minus 2. So the concentration of two are not the same. They are different, okay? But we know that it's perfectly balanced. So our electron neutrality will tell us that we have the sum, here it is. So here I'm writing sum of Zi, Ci equal to 0. You have Z plus C plus must be equal to minus Z minus C minus. Okay? So it means that in our case we have 1 CH plus equal to minus 2 CSO4. No, yeah, exactly. Yeah. So it means that the concentration of H plus is 2 times the concentration of SO4. It's okay, as expected. Do you agree? Okay. Now, but we know that the only flux we really have, is the one related to that H plus, because it's the only species that is produced on one side and consumed on the other side. Okay? So we know that the flux of flux plus of the H plus, here it is, must be equal to J Z plus F. Do you agree? This is Faraday's law. This is Faraday's law. So if we are, let me clean, and let's assume that we have a certain current density. We can measure it, and we can keep it. Okay? We have our system. We impose a certain delta V or a certain resistance in order to have a certain current density. We have a fixed current density. And we know that this current density is affecting the flux, is imposing a certain flux of H plus. While we know that we have no flux of SO4, the negative. So this is equal to 0. So we know that here is the negative electrode, here is the positive electrode, okay? So we have a certain flux, J, overall flux J. And this is related just to the positive charge in this case. Batteria scarica, getting low. Don't rely too much on electrochemical things. Don't trust. I can do this. Okay? Now let's look at what is the contribution of migration and diffusion. So you see some arrow here, but where they come from. So we look at our equation. So we have this one, okay? Now, using this one, we see that we can translate, this negative charge into a positive one. That's not a negative charge, sorry. The concentration C minus is related to the C plus. Okay? It's just a matter of Z, that they are constant. We know that the ratio is 2. We wrote it before, okay? So the ratio is 2. I can convert it. So let's imagine now I converted it. And this is, it becomes a plus, okay? And then here in front, what we have is Z plus I'm introducing here minus z plus divided z minus. Something like this. This check. Okay? Do you agree? Is that correct? Please correct if it's wrong. Okay. Now, what I'm doing now is summing up the two equations. Also here, sorry guys, also here, same thing. Plus, and here we introduce once again minus z plus divided z minus. Okay? Then I sum up the two equations. I would like to show you that this cancel out with this. This minus will cancel out with this. And so the two orange terms are identical, but the sign is different. For the rest, they are identical. So if I sum the two terms, this will cancel out with this. And here what in blue, here is the result. The result, summing up, so we have this guy, these two guys, they are right here. Sorry, this one is going here, while this one is going over here. And then here we have this one. Okay? I just managed to divide by d plus. Yeah, because, sorry, I had to move the d minus where it was. Yeah, there was a d minus and d plus that were different. So I divided this by d plus, so there was this passage I forgot to tell you. So I divided d plus here, and I divided d minus here. Okay? So I have a d plus here. Sorry. So there was another passage on the diffusivity. Anyway, sum them up and you get this. Okay? So, what's important from this one? What's important is that we have two terms with the gradient of C, and what they have in front are just constant. So what we're saying is that the gradient of C is equal to this guy here, J, that is constant at the moment, because we are imposing a certain J, okay? In all our system, we are imposing a certain J. So the gradient of C plus is constant. What it means? Linear distribution. Gradient is constant. Here it is. Gradient of C is constant. Linear distribution. Magic. And what about the negative? C negative. Same thing. Because we have this guy. You remember the ratio is 2. Fixed ratio, 2. So it means that the concentration of C plus is 2 times the concentration of C minus. No ways. You change the electrolyte, you change the number. But it's a fixed relation. So it's linear distribution of C plus, of positive charge, linear distribution, negative charge. This is what we are observing. Okay? But now, how is it possible that you have a gradient in the concentration and then the positive, we have a flux of the positive charge, but we don't have any flux of the negative? How is it possible? We have diffusion. So let's look at the four contributions here. So you have this contribution. Look at this. Let's look at the positive. This is this one, this green one here, okay? And this is in the direction, we have a minus, is diffusion, okay? So minus, so the gradient is like this, diffusion is like this, simple. We have the same thing for the negative. Also the negative will feel the gradient of the C minus, okay? So we have two diffusive flux from negative to positive electron. Okay? This is diffusion. But we have also migration. And what about migration? Look, the gradient they are opposite, that's the point. They are opposite. Okay? And what we know is that from this equation, they are compensating. This one must be equal to this one to give 0. So this migration term must be identical of this one, but opposed sign. So the two of them are compensating. Okay? So we have a gradient in the concentration, but we have also a gradient in the electric potential. And the two things balance the flux. Okay? But what about the positive? So this gradient, pay attention, let me clean. So the gradient here is negative if we have this as a x. Okay? So the gradient of phi is positive or negative? So we have, pay attention, we have a minus here. Okay? But we know that this is minus, this is negative, then we have a negative, so this flux is positive, and for us positive is like this. Okay? So we expect to have this, all this term here is negative to balance. Okay? So all this must be, if I exclude the minus, this one must be positive. Okay? But z is negative. So the gradient must be negative. Z is negative, gradient must be negative. So we know that the potential is going like this. We don't know exactly, so I make it bad, it's not linear. We don't know how it is. Of course there will be no way, so probably it will be something like this. Okay? But okay, I can rotate it a little. No, doesn't work. I can rotate it, okay. Something like this. Okay? So this is phi is going like this. Phi is going like this. So in this case, we said this is positive. If I include the minus, it becomes negative. Okay? But look, in the first equation, we have exactly the same, but z is positive. So we are changing the sign. Here it is. We are changing the sign. Because now z is positive. Very end. For the positive species, we have two contributions here. Diffusion and migration both play a role. For the negative species that is not involved in the electrochemical reaction, so we know that they don't participate to the current, they are compensating. Diffusion and migration are compensating. Okay? Let's go on. Let's look at current. Here it is, the phi I told you. So from the previous one, we can look at this one here. We can, okay, this one here, okay, this one here. A better description. And so you see that this green line is not linear, but this is the one we expected from the physical analysis at the beginning. You remember? Now, to look at the current is quite easy because what we have to do is just to multiply by ZF. So F is a constant, we are just introducing Z, we are changing or not our migration and diffusion term. Okay? So the positive, they will remain the same because we are multiplying by Z and Z is positive. So previous one, they were in this direction, you see them, okay? Going toward right, here same thing, they go toward right. What about the negative? The negative, they are changing the verse, the direction. So diffusion, in the case of molar flux, was pushing in this direction, compensated by migration. Here we multiply by a negative thing, so changing the direction. So now the diffusion is going backward and migration forward. Because, you remember, is just a matter of negative charge. So this flux is associated with this current, is negative. Okay? So quite simple. But they are still, of course, balancing. That's the point. Okay, this is the general case. Now, in many electrochemical systems, you have a solid electrolyte with fixed charge. Lithium battery, they have a liquid electrolyte. PEM fuel cell electrolyzers, PEM electrolyzers, solid oxide fuel cell, they have solid electrolyte. Now, many researchers are studying for lithium battery solid electrolytes. Okay? So, it's a very innovative, let's say, it's what many researchers aim at. In some technology we are already able to have them, in some other we are not, but people is working on that. So it's very probable that you will find in your life, if you work on electrochemical systems, solid electrolytes. That's the reason why we study that here, even in the general part. Okay, so now, solid electrolyte with fixed charge. Fixed charge, it means that you have a solid, it's a polymer, ceramic, or whatever it is, and in the material itself, you have some charges. Some radical, or some, let me say, groups in your material that they have a fixed charge. Okay? It might be positive or negative. The charge is fixed, so you don't expect to have considerable change of the charge, and it is uniform, homogeneous in all the material. So the fixed charge, here it is. Let's say that in our case is a negative fixed charge. And so in all the material you have a negative fixed charge. Some groups, for example, in the fuel cell, you have membrane with the SO3 minus group attached in the polymer. So you have always this negative group all around. Then you have electroneutrality also here, still valid. So the concentration of our ion, the ion that can move, okay? Let's assume is H+, might be something else, but let's assume is H+. You have electroneutrality. So also the concentration of your transport ion must be constant because of electroneutrality. So what's happening is that the gradient C is constant, C plus is constant, so the gradient of C plus is equal to 0. There is no change, no gradient of C plus. So this term cancel out. Very simple. And we are very happy about that. And so what we, of course, the negative equation, I don't write it because I know that the charges are fixed, so they cannot move. Okay? So I don't have this, and so what remains is this thing here. very nice law. And what if I look at it a little better, I see that all this thing here is constant. Z is the charge, F is F, RT, D the diffusivity. It might be affected by the concentration of C+, but this is constant, so no effect. Then I have C itself that is constant. So everything in front of my gradient operator is constant. So I give a name to it. The name I give is ion conductivity. This is ion conductivity. And the law I get is the Ohm law. Oh, come on, electrochemistry is incredible. You can obtain every law you like. This is the Ohm law. So you have the conductivity, the gradient of phi, equal to the current. Of course, you can translate the conductivity into 1 over the conductivity is the resistance, resistivity, okay? So you can translate it in a more familiar equation, but this is the Ohm law. And what's saying the Ohm law? Ion conductivity is constant. J, if we impose a constant J, a fixed J, a fixed current density, we have a constant gradient of phi. It means we have a linear distribution. Look at the green one. Linear distribution of the potential. Electric potential in our electrolyte. Ohm law. Okay? So we started for very complex phenomena, and then step by step, we are right here. Okay? So when you deal with the membrane, now you will see that you will deal with the membrane and say, okay, I use the Ohm law. It's not just because you don't know what to use and use the Ohm law. No, there is a theory behind it. There is a theory that demonstrates that the Ohm's law, when you have fixed charge in an electrolyte, works pretty well. Okay? And that's all for the electrolyte. So now we are able to deal with a complex electrolyte with more than one species going around, or we are able to deal with solid electrolytes. So we are able to calculate fluxes for the single species and related current density. Still alive? I see some reaction. No, I cannot make a reaction. Late. But if you remember, first slide, I promised. So ion transport, done. Double layer capacitance, done. Current in the electrolyte, done. We still have to deal with this. So we have half an hour, I think it's okay. We deal with this. So we're not talking anymore with the electrolyte. We're talking with the reactants. So the reactants must somehow reach our active area. Do you agree? And of course, going through, here we go. So let's go back to our electrode. And now the point is that we need hydrogen in order to have a hydrogen oxidation reaction. Once again, the same example. We need to have the hydrogen going and reaching the surface, moving through our electrolyte or whatever it is around. We have some electrolyte also at a certain point, and we need to reach the surface. Hydrogen arrives on the double layer, and then will react. Electrons will get in the electrode, and H plus will stay out in the electrolyte. Okay? Hydrogen must reach the surface. And you know that in our Butler-Volmer equation, we have the activity of the reactant. So the activity of hydrogen is influencing our reaction rate. Do you agree? So we have to know what is the activity of hydrogen here on the surface, not the activity over here on the tube where we introduce hydrogen. The two activities, the A bulk or A, I call it generally R or whatever it is, they are different. Do you agree? Here the concentration can be very high, the pressure can be very high. But then, what's the real activity here? What is the real concentration or the real partial pressure over there? Okay? So this is what we are studying now. What is the effect of this? And how we can estimate or calculate, evaluate the activity here. I anticipated that in every technology we will study, the transport of the reactants will play a role, even in batteries. Especially when you go to high current, low state of charge, the activity, so the concentration, for example, of lithium will be very, very important in determining the performance. Okay, now we are here and now we say, okay, let's have once again the Faraday law, but this case the Faraday law is for reactants. So we are saying that we have a certain current density. Sorry, this is supposed to be a J. This is supposed to be a J, sorry. We have a certain current density, and we have a certain flux of our reactant. It's not anymore the electrolyte, okay? It's our reactant. The reactant generally is not charged. In some cases it is charged, but in our case it's not charged. So here is not K, is not Z, the charge of our species, but what is that? This is the number of electrons that you are producing with 1 mole of your reactant. This N, I wrote it here, number of electrons per mole of reactant. Fine, okay? It's written over here. This is still Faraday's law, but it is applied to reactants, not charged species in the electrode. Of course, we can use all the same the equation we already used. So if we look at the black domain over here, once again, surface A, volume V, active area per volume SV, as before, exactly the same thing. We have a certain flux of hydrogen. The divergence of the flux of hydrogen, once again, is equal to the reaction rate. We are consuming hydrogen, so this gonna be negative, okay? We are consuming hydrogen. So we expect to have, if we don't look at this term, a flux of hydrogen going like this. Hydrogen is getting in our volume. Yes, of course. Pay attention that this J is the proton current. Huh? Okay. So we have hydrogen getting in. Hydrogen doesn't give any current, of course. It's a neutral species, moving in, no problem. Then, consider that once again you can have accumulation. And here we have the concentration of hydrogen. Yes. So concentration of hydrogen in our volume can change. So we can have some hydrogen accumulated there. And the concentration, as it was for H plus, is changed. Okay? So we have also here some transient. The transient will be, is not the same of the double layer. This is another thing. In that case, previous was the double layer because I told you the H plus accumulation was related to the double layer part. Okay? Now here we have hydrogen. It's another stuff. We have hydrogen dissolved, for example, in our electrolyte. But you can have something more complex than just an electrolyte, you will see, a liquid electrolyte. And here is our equation. So we can write, in the case of hydrogen, we can relate directly the reaction rate with our Butler-Volmer equation. So this is I is a current due to our Butler-Volmer. So I wrote it in terms of I and divided over 2F to go back to R. And here we have the accumulation term. Then I make an integral, so I go for a large volume, including the whole double layer, as we've done in the electrolyte case. So I'm integrating on the blue surface, and here it is. This is our automatic interruption. So I'm integrating this one, and so this SV will become the capital S. This is the whole surface of the double layer. Okay? And then what we are having here is a V, the volume, the whole volume of our system. Of our domain, the domain we are considering. And these C times V are the actual mole of hydrogen included in our volume. Okay? So they will change in time. And this is the overall molar flow in our system. So hydrogen is getting in from everywhere. This is the molar flow of hydrogen overall. Now, the accumulation term, when you reach steady state, it will be, once again, null, equal to 0. But when you have a transient, it is not equal to 0. And the typical time of this phenomenon is much, much longer than the one related to the double layer. Just to remind you that there are two different things. I reported here in gray the double layer. This is another equation. This is another phenomenon. Okay? And the double layer typical time is very short. I told you, millisecond. This guy here, this accumulation term, will get null in some cases in tenths of seconds or even in minutes. Okay? It depends on how big and how is the design of your system. Okay? It can be minutes. So it's two different things. You will see that we have some experimental techniques to make we can introduce in the operation on purpose a certain variation of the condition, and we'll look at the response of the system. And we know that the response of the double layer is pretty fast, while the mass transport phenomena are slow. So we can distinguish what's going on and make some diagnostic out of it. So knowing what is the typical frequency, the typical time scale of the phenomena. Okay? So we are going to use it in the so-called electrochemical impedance spectroscopy.
There's a difference in this domain.
Domain is the same, but the phenomenon is different. So one is happening in the double layer, the other one is happening everywhere. That's it.
Everywhere means the whole electrode.
Say it again.
I mean, everywhere in the sense the whole electrode.
Yeah, it's better we speak later. Okay, let's go on. I'm close to the end. This is the last slide, guys. Now, this is just to introduce the point. This is just to introduce the point. Then we apply, for the different technologies, we apply specifically mass transport equation to understand better. The point is, okay, here I put just a Tafel equation. You can also use the Butler-Volmer, is the same. But this is just to remind you that we have the activity of the reactant. On the positive, for example, in the case of a fuel cell, is oxygen. On the negative is hydrogen. So we have the activity of the reactants. And as I told you, the activity that is in this equation is the activity in the double layer. So it's not where you feed in the system your reactant, but it's the activity in the double layer. Okay? The point is, first of all, it's not easy to measure it. But for example, if you are in equilibrium, negative and positive, okay, you introduce hydrogen here somehow, and you introduce oxygen here somehow, but you can reach a certain uniform concentration of hydrogen and uniform concentration of oxygen. Okay? You can do that. It's quite easy. Or you can even flow it. So you have an inlet and an outlet, for example. Okay? There are different ways to do that. The point is, when you are not anymore in equilibrium, so you are drawing, current, really, the point is, you have a gradient in the concentration from the inlet to the active site, as I told you. Okay? And this gradient is mainly due to diffusion. If we take our Nernst-Planck equation and we apply to the reactant, what we have is that the diffusion term is still there. Okay? Because we can have diffusion of hydrogen and oxygen on our not charged reactant. Migration instead doesn't have any effect because there is no charge in our species. So they are not affected by the electric potential of the electrolyte. Okay? So the term of migration is not present. Then we have the advection term. Okay? Of course, we can find a way to flow flow macroscopically our electrolyte or our reactant to flow towards our active site. So we have diffusion and advection. These are the two main phenomena involved. But sooner or later, diffusion will have a role. So locally, it depends, of course, on how relevant is the advection, but sooner or later, you will have a gradient in the concentration. Okay? And the gradient in concentration will give a gradient, here it is, in the activity. Because I remind you that activity and concentration are strictly related. So, the flux of, now let's stay with the hydrogen. The flux of hydrogen is J over 2F. We are imposing a certain J, so we know the flux. But this flux, if we are assuming that diffusion plays a role, is somehow I put a proportional to a diffusivity of hydrogen divided at a certain relevant length. Okay? Depends on how long is the pathway of diffusion. I mean, if all this is given by diffusion, it's a long path. But maybe you are able to flow with the advection till here, and so the diffusion will be just like this. Okay? Depends on how is the design, the geometry of your system. So there are different possibilities. But sooner or later, close to your active surface, you will have diffusion. Sooner or later, you will have it. Okay? So the relevant length can be longer or smaller, depending on geometry, but diffusion plays a role. And so diffusion will determine, as I told you, a difference, a gradient in the activity, so a difference between the activity you have in the bulk and the activity you have on your reactive site, reactive surface. Okay? Now the point is that, so if these equations are true, what's happening is that you have a maximum J you can draw. There is a maximum. Why? At a certain point, you increase J. Look at this equation, sorry. Look at just at this and this. Increase J, and the bulk, let's assume that the bulk filling is fixed. Okay? So I'm introducing here a fixed activity, fixed concentration of hydrogen, or here, depends on how good I am, but it's fixed at a certain point. Okay, so this is fixed. If I increase J, I have A on the active surface is decreasing, of course. There is a limit. The limit is that the activity goes to 0. There is a maximum J that will determine the activity tends to 0. And this maximum J, here it is the limiting current density. This is the maximum current density you can draw in that system feeding that activity, that concentration of reactor. There is a maximum current density. And why is a maximum current density? Look at your Tafel or Butler-Volmer equation. If this value goes to 0, what's happening? The logarithm is going to minus infinite. Do you agree? Yeah, then we have a minus here, so our overpotential is going to infinite. So our hydrogen overpotential is going to infinite. And what about the oxygen? Same thing. There is a maximum, there is a minimum AR going to 0, minus infinity, this is a plus, so this goes to minus. The overpotential of the positive is going to minus. And here is what's happening on our polarization curve. So this is the theoretical value. Okay. Then we have this one, the black one over here is including. This is including everything: overpotential of the positive, overpotential of the negative, the electrolyte loss. Is introducing everything, but so far with this black one here, A of the reactant was fixed, constant. Now we are introducing a further loss. This is not very nice. The graph is not very nice. I will make a better one. Anyway, we are introducing a further loss. The further loss is the green one depicted here. This is related to the fact that A is a function of current, J. Okay? This is what we are saying here. This is exactly what we are saying. Okay? A is a function of J. So, the higher the current, the lower will be the reactant activity on the active side. At a certain point, you will reach the maximum current that is acceptable, the limiting current. When you reach the limiting current, you cannot go farther. Okay? Your potential is going to be, as I told you, one to minus infinite, the other one to plus infinite. So the loss will be positive and very high. So you see that we have some limits. When we deal with high current, we really have to pay attention to have the right amount of reactance. From the practical point of view, you understand very easily. I need to feed a certain flow of hydrogen, for example. If I fix a certain flow or certain concentration, so yeah, let's say I have a maximum flow of hydrogen in my system. Every mole per second will give 2 electrons per second. So if I don't feed enough hydrogen, I cannot have high current higher than a certain value. That's the point. So we have to deal with this. And this is, as I told you, very related to the design of your system. So we don't go through the details of that today. In some books, you will find that they will call concentration losses or things like that. I really ask you to pay attention, because you've seen that what's ruling here is still the kinetic. So it's Tafel or Butler-Volmer, but that in the kinetic you have the activity. Okay? And then you have to introduce diffusion or whatever is a transport phenomenon. Okay? And they will affect the activity. So it's just applying mass transport coupled with the kinetics. But this is not something not depending on the kinetics. It's related to the kinetics. So the idea to separate the losses, kinetic and mass transport losses, I don't think it's so, can be misleading. That's the point. So in our case, we don't distinguish them. They are involved. They are coupled. They are coupled. Okay? Then we can say, okay, this effect is mass transfer related. It's mass transfer related issue. But we don't calculate our loss for mass transport and our loss for kinetics. Okay, guys? That's all. For those of you who like, they can take a look at the homework. I just would like to tell you that during the course, we will answer during the lesson, during some exercises,